Assalamu alaikum. Today we are going to talk about topological sort. We will start with an introduction to graph. We'll talk about type of graph, how does graph represented, and graph traversal algorithms, depth first search and breadth first search. Then we'll move to our main topic, topological sort. We'll define the topological sort, where it's used, how it is work, what are the algorithms used to perform topological sort, and we will analyze both of them. Then we will conclude our presentation, which I hope you will find it helpful and interesting. At the end of this presentation, you will find the question we were asked to prepare, and we will discuss the answers together. What is a graph? Graph is a nonlinear data structure made up of two main components, which are nodes and edges. In this example, we have 5 nodes and we have 7 edges. It is an undirected graph. We don't have an arrows on the edges, so it is undirected. So when we talk about graphs, we are talking about vertices and edges. Vertices has what we call a degree, and we will talk it and discuss about it in a little bit. We have edges, two types of edges, directed edges and undirected edges. When we are talking about directed, we have a source and a target node. So the way we can traverse the nodes are specified. The degree of a vertex is the number of edges that are incident to that node or vertex. We have mainly two types of degree, in degree and out degree. The in degree, which are coming to the node, and out, which are from the node. The table below shows the in and out degree or the nodes in this graph. As we can see, node 3 or node 3, for example, have one out degree and one in degree. Some of the concepts we need to remember is the meaning of adjacent vertices. Adjacent vertices, they are neighbors, okay? There's an edge, direct edge between them. For example, node 2 is adjacent to node 4. Also, we will talk about what the definition of a path. Path is the way or the mean we can use to traverse from one node to another that does not have a direct edge. For example, if we are going to move from node 1 to node 3, there is no direct edge, so we can use the edge from 1 to 4, from 4 to 3. There are so many classifications for graph, depending in many criteria. I just mentioned few of them that we are interested about: directed graph and undirected graph, and we have just explained it. And we have what we call weighted graph. Weighted graph is a graph that has weights on the edges. It could represent distance, cost, depending on the problem we are dealing with. How we can represent graphs? Graphs are represented mainly in two main ways: adjacency matrix or adjacency list. In the first representation, we will construct a matrix, the number of the rows and columns equal to the number of the nodes. Whenever an edge exists, we put 1. If the edge does not exist, we put 0. For example, A and B, they have an edge between them, and it is undirected graph, so we will find it A, B, okay, and we will find it in B, A. A does not have a self loop, so A is a 0. However, B have a self loop. Okay, so we find B has 1. The other example shows the same graph when it is directed. Okay, so we'll see that number of ones are less now, but we can put it both ways. The other type of presentation can be used for graph is a linear list, as we said, or lists. Lists can be represented as an array or a linked list. In the linked list, we will have linked list with a number of nodes, and each node will point to the node that it has an edge between them, where the last one is pointing for none. In the same way, we can use an array to represent the graph. Graph traversal algorithms are, what do we mean by traverse the algorithm? We mean to move from node to node through the edges. There are many algorithms. Search algorithms are used for traversing the algorithms, mainly breadth first search and depth first search. We all know both of these algorithms. We will come to a quick notes about them to remember how do they work. Breadth first search, for example, from the name, okay, it's move level by level to traverse the algorithm, and usually in the implementation to maintain a track of our traversing or moving through the graph, we use a queue. The other algorithm is the depth first search. In this algorithm, we move as far as we can to reach the leaf nodes, and we will start backtracking when to continue moving through the graph. So 1, 2, 4, 4 is the leaf, then 5, backtracking to 3, and finally node 6. Usually for implementing this algorithm, we use a stack. Now, after we are reviewing some of the terminologies we are going to move to our main topic, which is topological sort. Topological sort is the process of arranging vertices in a directed acyclic graph. How we arrange it? Linearly, in which we have a condition. If we have an edge u to v, then u should appear before v in the topological sorting list. Let us stop a little bit on the definition. We have 3 conditions that we have to maintain so we can find our topological sort. The first condition on the type of graph, it should be directed and acyclic. Acyclic, what does acyclic mean? It means that it does not have a cycle. Also, we have to maintain the condition that when an edge exists between u and v, u should appear before v in the topological sorting array or list we will have. Topological sorts have many applications. We can use it in project scheduling, dependency management, finding the graph cycle, deadlock conditions identification in an operating system. Also, it has an application in finding the shortest path in the weighted acyclic graphs. Okay, let us look at this example. Consider this graph. What do you think is the topological sort for this directed graph? We will start with the first node, which has no n. edges, yes. So 1, then we can choose between 2 and 3. Then we move. So 1, 2, 3, 4, and 5. So this is how our topological sort list will look finally. Topological sorting for a particular graph can be sorted in multiple ways. For example, in the previous example, as I said, we can choose between 2 or 3 to put after the 1. So we have 2 topological sort for this simple graph. And you can imagine that when the graph is more complicated, more options will be exist. So if we took this second example, it's more complicated. All of these lists are a topological sort except the last one, the red, which is not. Okay, why? Okay, it starts with 10, and 10 depends on 3 and 11. We evaluated the condition that says that if U pointed to V, U should appear before V in the topological sort. Okay, let us examine this example. What do you think is the topological sort for this graph? As you can see, we cannot perform topological sort in this graph. Why? Because it has a cycle. When a graph has a cycle, I can't decide where is the dependency. So I should put B before C or C for D, D before B. They are all dependent on each other. And it's violated the condition, as if you remember, we only perform topological sort on DAGs, directed acyclic graphs. To find the topological sort, we need to use an algorithm. Mainly, there are 2 algorithms, the breadth first search and the depth first search. Okay, topological sort using the breadth first search. Just recall, the n degree of a node is the count of incoming edges for that particular node. Okay, these algorithms use the n degree to perform the topological sort and find the list for the algorithm. The steps we need to follow are listed in the slide. Find a vertex that has n degree equals 0. Remove all outgoing edges out degree. Add that vertex to the sorted array and repeat till there are no more vertices left. So let us move to an example that explains how does the algorithm work. Just keep in mind that breadth first search use the n degree to perform the topological sort. For this graph is shown, it is directed, acyclic, no cycle exists. Okay, so we can perform topological sort. The tuples above each node represent the n and the out degree for each node. So let us follow the steps and see how our topological sort will look like. To start with, we should start with the node that has n degree equals 0, which is A. So A will be our first node. And the algorithm says that we should remove the outgoing degree edges. Sorry. So we will decrease the n degree of these nodes by 1. So this is how it would look like after we removing the first node and we remove the out degrees and we decrement the n degrees of these two nodes. Then we could choose between any of these two algorithms. Start with C. Same way, we remove the outgoing edges and increment the n degree of the destination nodes. In node B, remove the edges, increment the n degree for the destination nodes. D, it's 0. You will always choose the node with the n degree equals 0. Finally, so this is how our topological sort list look like. So if we move to the second algorithm, depth first search, the depth first search works on the adjacent list and adjacent nodes as we explained earlier. Okay. The second difference between the previous one, it starts from node 0 to node n in a for loop, okay, and store the results on a stack. So we'll go through all of these steps in the next example. So at first, we will have an array, which we call a visited array. All the nodes will be initialized in the array with a false, that they have not been visited yet. Also, we will prepare what we call adjacency list, which says each node has direct edges with what other nodes. For example, node A has direct edge with C and B. B has with D and E and so on. And we will have the stack where we will store our list. So the first node to start with will be A. In such algorithms, always we will be given how to choose the priority. Okay. For this example, we will assume that we are going alphabetic order. Okay. So the first node will be node A. So we will find the DFS for A. A has direct connection with. So sorry, we first find the DFS for A, and we will mark A as visited true. Then A has a direct connection with C and B. As we said, we were going through alphabetic order, so we'll choose B and mark B as visited, then C, and we will mark C as visited as well. We are at node B. Is B the leave node? No. So it has a connection from the adjacency list. We can get it. B has links with D and E. So we will find the DFS for D and mark it as visited. And we are done. D in the adjacency list has no adjacent node, so we can add it to the stack. Okay, continue. Find the DFS for E. E has an edge connecting it to F, so we'll find F, mark F as visited. F has no more adjacent node, so we can add it to our stack. Okay, F done. So we start backtracking. E, it's done now, remove it. Then backtracking to B, C, and finally node A. So the topological sort list will look like A, C, B, E, F, and D. For topological sorting algorithm analysis, we can find that time complexity is big O of V plus E, where V is the number of vertices and E is the number of edges. And this is explainable because we have to visit all the nodes. We will move over all the nodes or vertices, and each edge will be analyzed, so worked in, so it's V plus E. Space complexity is big O of V, which is the number of vertices, the stack or the queue we use to store the results. Keep in mind that in some references, you will find an auxiliary space complexity for the adjacency list and for the visited array. However, it is small and could be ignored. Conclusion. This presentation aims to introduce the importance of topological sorting. We have seen these algorithms work only with directed acyclic graphs. Moreover, we have seen that graph may have more than one topological sort. Topological sorting have many applications in computer science, and it is very useful. The question about the topic of topological sort is as this. As we have discussed the topological sort, which can be performed using paired PFS or DFS, and has many applications in computer science. Starting from that, what if we take the next step and compare the performance of both of the implementations of the topological sort, namely using loop-based and a recursive? Do you think it will be different, or one will be performing better than the other implementation? Actually, after implementing both of the algorithms using Java, they found that the time complexity and space complexity are the same for both algorithms in both of the implementation. No changes found. However, in the loop-based approach, we use a queue and a visited array to keep track of the visited node and process them in the BFS. This approach can be more efficient for sparse graph. In the recursion-based approach, we use a stack to track the order of the visited node and process them in the DFS. This approach can be more efficient for dense graphs. For the space complexity, both of them is big O of B. However, as I said, the loop-based approach may require additional space for the queue and the visited array, while the recursive-based approach may require additional space for the stack. The finding of this question shows that it depends on the type of the application and the problem I use, which reflected on the graph, if it's sparse or it is a dense graph. So finally, this is a table to compare between both approaches used and how they are differ. As we said, to conclude, loop-based are better for sparse graphs, while recursive-based approach are best for dense graphs. Thank you all. I hope you enjoy this presentation and finding it helpful.